calculate the volume enclosed by the following things. A sphere of radius r smaller than or equal to 3 on the top, so that is like the top thing that encloses this volume, and the cone z squared bigger than or equal of x squared plus y squared on the bottom. So this could be perfectly a problem in an exam. Okay, calculate this volume. The first thing that I would ask you is to sketch it. Okay, maybe sketch a cross section or something like that. So you have to imagine the sphere and the cone given by z squared bigger than or equal to x squared plus y squared. Okay, so how can you figure? I don't want to spoil you by showing the figure, which is here. So how can you figure out what this cone looks like? Well, if you take the square root in both sides, you could see that z is bigger than or equal to the square root of x squared plus y squared. And you also know that the square root of x squared plus y squared is just the distance to the x-axis, to the z-axis, right? It's what we usually call rho. So z is bigger than or equal to rho. Okay, so the distance to the z-axis. Which means that if you plotted, now you have seen what it looks like, but if you plotted rho versus z, then z equals rho is this line, and we are saying z is bigger than rho, so this is this cone here. And this is in the axis z rho, but of course rho is pointing away from the z-axis, so we can do the revolution around the z-axis, and we find this cone here. Okay, so this is z equals rho. That's the surface of this cone. Now on the top we have the sphere with radius equals 3. Okay, so this surface here, as indicated here, is the surface given by r equals 3, where r is the distance to the origin. Okay. Now, how do we integrate this? We could choose rectangular coordinates, and it would be a mess. We could try cylindrical coordinates. I think it would also be very complicated. It would be easy to do the cone part, but it would be very difficult to do this spherical cap. So clearly the best option is to use spherical coordinates. Okay, so we need to use spherical coordinates. Which means that we're going to find the volume by integrating along r, theta, and phi. Okay, so the volume is going to be the triple integral of dv, and we remember that we know in spherical coordinates dv is r squared sine theta dr d theta d phi, right? You can look it up if you don't remember. You always have tables in the exam where you can look up dv in any coordinate system. So we substitute that in, so we have to integrate r squared sine theta dr d theta d phi. Now we need to find the limits of integration. So what are the limits in r? So what are the values of r? So the trick to find the limits in r is you draw a line in the direction of r, and you think about when this line enters the region of integration and when it exits. Yeah. So clearly it enters the region of integration at r equals 0, and it exits the region of integration at r equals 3, which is this surface here. Okay. So r goes between 0 and 3. Now phi is the angle with respect around the z-axis, yeah? So it's the angle with respect to the x-axis, but in the xy plane. So clearly this angle is going from 0 to 2 pi, okay? So phi is going from 0 to 2 pi. And finally, what about theta? So theta is the angle with respect to the z-axis, okay? So this is this angle here. Let me show it to you. So it's this angle here. This is the angle theta, right? So clearly the angle theta goes between 0, which is in the z-axis, up to a maximum angle that we have to figure out. So how do we figure out the angle? So if you look at this cross-section of rho versus z, So theta is this angle here. Oops. So theta is this angle here. That's the maximum theta, right? So theta goes between 0 and this angle. But if this has a slope of 1, because this is the equation z equals rho, this means that theta must be 45 degrees. Or in other words, it's pi over 4. Okay? So we can find the limit of theta to be from 0 to pi over 4. Okay? So therefore, our volume is equal to the integral 0 to 2 pi, 0 to pi over 4, 0 to 3 of r squared sine theta dr d theta, which we can apply separation of variables. Okay, which we can now solve, very similar to calculating the volume of a sphere. And the final answer to this is simply, if you work it out, it's 18 pi times 1 minus 1 over square root of 2. You will have to calculate the cosine of pi over 4. Yeah. Okay. So this is this problem. Notice that we have done problems in spherical coordinates when the limits are always constants. But the same way that you could have non-rectangular regions in x and y, you remember all of this, right? So in x and y, sometimes you could have non-rectangular regions, and then the limits were functions. So the same thing can happen, for example, in spherical coordinates. And I have lots of examples of that in the problems. Since you already have lots of videos to watch, I didn't want to record a video for each problem, but in the problem sheet I can see you have at least 23 different problems. Okay, so you can see all sorts of different integration regions. For example, you have problem 20, where you have to calculate the volume of a cone, and therefore, for example, if you use cylindrical coordinates, so then the surfaces are functions, as you can see. Yeah. So that is, of course, with all the solutions, but you can see that the limits are functions, but we are still integrating in for example, in this case, cylindrical coordinates. You also have the problem we just did. You also have this nice problem of this very strange shape. So now in finding the limits, one of the limits is a function of rho, and so on. Yeah. So you have lots of problems in the notes. So please go through the notes and look at all these different problems. Thank you very much, and see you soon.